Okay, we're doing this path integral quantization. And we got so far as to find out that to restrict the path integral, we wanted to insert something. We wanted to insert, so z was the integral dA, e to the I action, and we wanted to insert 1 in the form of some delta function constraint that constrains the path integral, and delta of A was the determinant, the partial of f with respect to theta. Let's put a theta on there. There's in principle a theta on there, and that's an identity. Well, we did a reasonable job of doing a one-dimensional constraint. What I didn't do is I didn't do why is this determinant there. Okay, we know there's something. We in our one-dimensional example we had a change of variable constraint, and it really is a change of variable constraint. Let's just do this with two variables and two constraints. Okay, so we want to generalize what we had before from one variable to two. So it's some du1, du2, some constraint delta of f1 of u1, u2, delta f2 of u1 and u2. So what's the right, the math question is, what is delta? Okay, and so if we had a simple constraint, so let's do dx1, dx2, delta of x1 and delta of x2. That of course is 1. So as we work away from that, if we change variables, this is we're going to then change to x1 is some f1 of u1 and u2, x2 is f2 u1 and u2, so new variables. And we know when we change those variables, if we have any integral dx1, dx2, f of x1, x2, that turns into the integral du1, du2, f of f1 and f2 of those guys times the Jacobian, and the Jacobian is the determinant of the partial of f1 respect to fi respect to uj. So there's our determinant. It's a change of variables. So if we go back up here and we plug this in, this turns into then the integral du1, du2, determinant partial fi respect to uj. times delta of f1 of u1, u2, delta f2 of u1, u2. So it really is just the Jacobian. I use that phrase. So here's the Jacobian of that transformation. Okay. And of course, we're generalizing this now to an infinite number of variables. There's one for each point in space-time, so there's an f at each point. And if there could even be a few f's at each point if there's a lot of gauge fields. Like in non-abelian theory, there's n gauge fields at each point in space-time. But it's the Jacobian, the determinant of everything. Okay. Then we showed very quickly that delta is independent of theta. So that factors out. And that lets us then factor out integral d theta, the path integral of the theta, which is infinity, but it gets factored out, and we're left with a constrained integral. We're left with z is the integral dA, the determinant of df d theta, delta of some f of a e to the I integral d for x L plus the JA. Okay. So we've got the constrained guy. Okay. So our tasks at this stage are to make sense of these two guys. How do you do a path integral with a constraint, and how do you calculate the determinant? Okay. Well, let's first do QED because it's the easier one. Let's take a look. Let's try the following gauge. Let's take f of a is d mu a mu minus some constant. Okay. Clearly, f is equal to 0 is a typical one, but there's a reason for sticking it in here for later work. Okay. Then if we have f of a of theta, remember a mu goes to a mu plus or minus d mu theta is the gauge transformation. This turns into then d mu a mu minus box theta minus f. So our beast that we have to do, this df d theta, is just the D'Alembert up to a sign. Let's not worry about the sign. So our delta is df d theta with the determinant, so I need my determinant, is determinant of box, which at the moment all we need to know is it's a constant with no A dependence. Okay, so it is just a number. And we're actually going to make sense of that number a little bit better because we have to do it for non-abelian theories. But for QED, you can just drop this. Okay? So there's no particular thing there. So in QED, we then just have z of j is the integral dA delta of, in this case, d mu a mu minus f, e to the I integral d4x. And let me write out this guy for a moment. There's a 1/2 a mu box g mu nu minus d mu d nu a nu j mu a mu and because of that delta function constraint, the piece that sits there is just a constant. Then take a derivative. So here's d nu a nu is a constant. Another derivative gives 0, so that doesn't bother anything particular. And then we should be able to do the usual trick. We shift a prime mu of x, a mu of x, plus integral d4y df mu nu x minus y j nu of y. And under one condition, we end up with then z is z of 0 e to the minus I over 2 d4x d4y j dj. Okay, the usual piece. You can fill in the blanks. Okay, the one condition we do have to check is that d mu a prime mu is also equal to minus f is equal to 0 also. In other words, this satisfies a particular gauge condition. This needs to also, and so we have to check that. Okay. So it's actually pretty easy to see that the condition is just that the second piece there gives 0. The first piece gives the gauge condition. This one will if that guy gives 0. So actually there's a little condition on that. We have df mu nu is integral d4x d4k over 2 pi to the 4th minus I g mu nu comes out from just integrating the box. The g mu nu is what I'm after. Okay, so the g mu nu tells us that when I take d mu on df mu nu, okay, the mu and nu indices become the same. So if I take, actually what I really want to do is I want to take j nu of y integral, this is d by dx and d4y. Okay, that's what I'm taking the derivative of. That turns into the integral d4y. Once I'm under the integral sign, I can make that dy mu j nu of y. And I can then integrate by parts. A equals integral d for y. I'll just write this as df with no mu nu on it. And it becomes d nu, j nu of y, which is 0 by current conservation. Okay, so this overall equals 0, and we have d mu a prime mu equals d mu a nu, which is what we need, d mu. So this ends up then with the usual Feynman rules that I gave you to start with, g mu nu k squared plus I epsilon. Any questions about that part? Some people are still writing. All right. Next trick in the book, covariant gauges. Okay. We inserted delta function of d mu a mu minus f. This is a function of position, so there's really a delta function in each position. There's no reason we couldn't use a different f at each position. So we could go to delta of d mu a mu of x minus f of x. We could have done that. It still factorizes, everything still works out like before. So there's an alternative choice. So we could also take various combinations of that, and here's the covariant. There's another trick. We, instead of just inserting that, we do that and we integrate over them with some weight. So integral df delta d mu a mu of x minus f of x, and we use the weight e to the minus I over 2c integral d4 x f squared of x. So it's sort of like a Gaussian weight. So with this Gaussian integral, when we do the delta function constraint, we get e to the minus I of 2c. Basically, f squared gets replaced by d mu a mu. D mu a mu squared. So what that does for us, we now no longer have the delta function constraint in the path integral. We're still doing the path integral over all a's, but we have a modified Lagrangian. So it's e to the I integral d4x. We start with 1/2 a mu box g mu nu minus d mu d nu A nu. This new piece has been added as 1 over 2c d mu a mu squared, and then, there could be j mu a. Okay, this piece here can be integrated by parts. If you integrate it by parts, it also looks like a mu d nu a nu. So you take one of the derivatives from one of the a's, flip it to the other, and it looks like that. This then has an inverse, and you can see the inverse. So in momentum space, d f mu nu is I over k squared plus I epsilon. There's a minus g mu nu plus 1 minus c k mu k nu over k squared plus I epsilon. This is the propagator now, and if we take c is equal to 1, it's Feynman gauge. If you tried to take this term and set it equal to 0, you would take c goes to infinity, it blows up. But we already knew that there is no inverse when you drop this term, so it's no surprise. When you calculate with this parameter, you can do the calculation for general c, and c drops out at the end. It's a great way to check that your calculation is correct, because if you miss a minus sign, it's never going to happen. Okay, so that gives us another way to get these propagators out, and it has a whole class of gauges which are often called RC gauges. Okay, so we now want to go on from QED, which we've, at this stage, solved completely. And to do that, I want to first review what's another trick for dealing with the determinant. So this is the Fadeev-Popov trick. Okay. So we'd previously taken, if we had the determinant of some fancy object, we wrote this as e to the trace log m, which was e to the integral d4x, x log m, x. And I'm sure this was tried for the determinant that was the Jacobian there, but it's not very effective. Here's another trick. So recall the fermion path integral. We have integral d psi bar, e to the I integral d4x, psi bar operator psi. That turned into some number times the determinant of this operator. So Fadeev and Popov run it in reverse. If we have some determinant m, we can write it in terms, we can imagine some new fields. We'll call them c and c bar, and write this as e to the I integral d4x c bar m c. So in this case, c and c bar are fermions. Their c and c bar are going to be called ghosts. They're not real particles, so they don't live in the external state. So we don't produce them. But if they enter this path integral this way, We'll then have some Feynman rules for them. They'll end up propagating in loops. And I should recall it the fermions. Okay, so if we do this, we had previously this function, this determinant in z of j. So we can now write z as dA, dc, dc bar, all path integrals. There's the delta function constraint of f of a. But we now exponentiate the rest of it. So we would have e to the I integral d for x, the usual Lagrangian, plus c bar, the determinant was df d theta, c. So if you recall in QED, we calculated df d theta is del squared. So the ghost Lagrangian then is c bar del squared c. Yeah, it looks sort of like a regular Lagrangian. You can integrate this by parts. It'd be minus d mu c bar d mu c. There is a minus sign there. Doesn't play too big a role, but that's part of why it's called a ghost. It has the wrong sign if you write it in this form. But still, it looks like a pretty normal Lagrangian other than that. So this lets us then immediately do the non-abelian case, the Yang-Mills case. And if you remember, our small gauge transformation there was if I had a mu prime, that was a mu plus 1 over g d mu some alpha a minus f a b c a b mu alpha c. So here in our example now, our notation goes alpha a goes to theta a. So if we have a constraint f of a being something like d mu a mu minus f, then f of a of theta is d mu a mu plus 1 over g d mu theta, okay, minus FAB C, AB theta C. So if we calculate our determinant, we have the f d theta, so the constraint on theta A, is 1 over G delta AB box, just like in QED, minus FABC ABC, it's actually ACB is really what it is, D mu A B mu. Okay. So if we write the ghost Lagrangian, in doing this, I'm going to rescale 1 over G C bar C goes just C bar C, just the normalization changes a little bit. Then our ghost Lagrangian is C bar A delta A B box, and I guess it's plus F A B C E mu A C mu C B. And there's a G now because I've rescaled. Actually, I'm sorry. I missed my 1 over G's. The 1 over G just sits in front of that first term. The second term doesn't have that. So I can compensate by putting a G there. Okay, so in this formula, just like the derivative acts on things to that side, this derivative acts on both of them. It acts on both A and C, so it's the sum of them. So, but now this looks like an interacting Lagrangian. It's no longer independent of A, so we're going to have some interactions now. In particular, there's an interaction that takes this C field a gluon, which we'll write out the Feynman rules for. Okay, so here's that we've then now got the constraint there in terms of these ghost fields. And I just want to comment about the physics before we go on. There's a bit of, you can see it from the history a bit. Historically, the ghosts were first proposed by Feynman. In quantum gravity. Around 1961. And he actually effectively quantized gravity at around that time. But the issue that he was facing is that the gravitational field, it's called h mu nu, is like part of the metric tensor, has 2 physical degrees of freedom, 2 physical propagating degrees of freedom, like any massless field. But h mu nu is symmetric, 4x4 matrix has 10 components. So when you're dealing with external states, it's not an issue. You just prepare the physical external states. But when you're dealing with loops, there's too many degrees of freedom in the loops. You have an extra minus sign. That has these fields canceling off the unphysical stuff. Very clever idea. The extra minus sign comes from fermion loops. If you remember in Feynman rules, anytime you have a closed fermion loop, you get an extra minus sign as part of the Feynman rules. So if you put something in and make it a fermion, it cancels off something. There's actually another way to see this. You know, the boson determinant goes like 1 over determinant of some operator to some power. The fermion determinant goes upstairs, and so if you choose your stuff right, then there's a cancellation between the upstairs and the downstairs of some of the components. There's a lot of components, so this determinant gets raised to a large power. So that was the original impetus, and that's the physics behind it. DeWitt very soon after made it more formal, and then Fadeev and Popov picked it up for gauge theories. So basically the idea is that the gauge loop minus the ghost loop ends up being the physical results. So let's just explore these ghosts a bit. So there's one for each gauge field. So CA, A equals to 1 up to n squared minus 1, because there's n squared minus 1 gauge fields. So it lives in the adjoint representation, just like the gauge fields do. The free Lagrangian is C bar A box CA, so the propagator is I over P squared plus I epsilon delta ij. So we just have this draw it typically by dashed lines. It's massive like the gauge bosons. But you notice this is odd for fermions. It's not I del slash like we normally have for fermions. So the kinetic energy piece is wrong. So in some sense it doesn't look like your usual spin statistics connection that you would expect. You don't get the Dirac equation. The place it only propagates is in loops, so the most important application is in something like wherever you have a gluon loop, like the vacuum polarization, you also end up having a gauge boson loop. And let's see, what else do I want to say? I want to then say that the final Yang-Mills-Lagrangian then has, well, we would do the covariant gauge trick, and we'd end up with the Lagrangian being minus a quarter F mu nu F mu nu minus 1 over 2c d mu a mu a. These are a's, they run over all of them. A mu squared, there's a psi bar I d slash minus m psi. There's the minus d mu c bar, d mu c, the ghost piece, and then there's the ghost interaction, which is minus g f a b c d mu c bar a b c c. Okay. What I've done here is I've actually integrated by parts. In this, previously the derivative acted on both a and c. I integrate by parts. It acts just on c bar, so it acts on the outgoing field. So the Feynman rule that you'll see come out has only the outgoing momentum in the Feynman rule. So let me finish this unit by writing out the Feynman rules. For Yang-Mills. Okay, so recall that F A mu nu is d mu a nu minus d nu a mu minus g F A B C a mu b a mu c. So when I do f squared, I get f0 squared, the piece with no interactions. There's then a minus 2g f a b c f 0 a. Let's leave off the indices at the moment. And then there's a g squared f a b c f a c d a piece. You see that the first order term here has a derivative acting on an A field, so when there's a triple interaction, AAA, there's one derivative. When there's a quadratic, there's no derivatives. So then, the Feynman rules are, if we take a fermion, we get minus IG, gamma mu, mu is the index of this field, lambda A over 2. And you note that there's actually two different spaces going on here. One is Dirac space, so the Dirac indices might be some alpha beta. There's another, the color space, IJ, and you have to keep the order correct for both of those. The order matters because these matrices don't commute. But typically you leave off the indices and just write them in the right order and use matrix multiplication to define them. If we have a gluon coming in, to be a little bit more careful in the labeling of this because the momentum counts. It's mu is the Lorentz index, A is the color index, P is the momentum. I'll make this Q, momentum, nu is the Lorentz, and B, and this guy I'll draw going in, R lambda, C lambda is the Lorentz index. So this is minus G F A B C. There's no I because the derivative brings also a factor of I. G mu nu P plus Q lambda minus G nu lambda R plus Q mu plus G lambda alpha G lambda mu R minus P nu. So the way we've written it here, the momentum label involves every momentum except the one that the Lorentz index falls on, so the lambda involves P and Q. So anyway, that you can write it out. The ghost Lagrangian also has to be labeled, so if I make this P, P, and I'll put color label B, R, color label C, and the gluon coming in is color label A, momentum Q, and index mu, Lorentz index mu. This is G, F, A, B, C, R mu. So it's the outgoing particle's momentum is what enters it, and only that. And lastly, I won't write out all the terms, but just to show you what they sort of look like. There's some A mu B nu C lambda D sigma. Quartic coupling, it's minus I G squared F A B D F C D E G mu lambda G mu sigma minus G mu sigma G mu lambda plus permutations. Okay, you can look it up, but it basically has no momentum factors. It has a bunch of indices that get contracted up just because the original thing gets contracted up. There's some anti-symmetry that's built in, and that describes it. Okay, let's stop there. We'll come back next time and talk about the Ronin coupling.